Hello, welcome. Happy, what's today? Wednesday. Yeah. All right. Hope you're all doing well, staying healthy. Yeah. Um, as of right now, I'm not planning on doing office hours until Monday, but if you just need to talk or you have questions, message me. Yeah, either through Google Classroom or you can do it through Remind also, and I'll get your text and we can set up a little meet. Okay. We will get through this. Every day is a new day. Things are changing every day. I don't know what's going to come, but we're going to go with it. Yeah. All right. So we did 4-3 yesterday with diagonalization and stuff. Today we're going to do some symmetric matrices. So section 4. So let me start this. If I do this before I start the video, then it doesn't work. Not yet, anyway. I'm still learning. So eventually, maybe I'll figure out a faster way to get this done. But as of right now, there we go. Okay. So here is section 4. I'm not going to rewrite all of these lemmas and theorems. I'll just talk you through them. All right. So start off by saying, recall that A is symmetric if and only if A is equal to A transposed. And all that means, A transposed means you're going to switch rows and columns. So you'll take row 1 and turn it into column 1. Take row 2, turn it into column 2. Take row 3, turn it into column 3. That would be A transposed. You switch your rows and columns. And if the two are equal, if once you transpose it, it's equivalent to the original matrix, then we call the matrix symmetric. And so then it says, let A be an n by n, so a square matrix that's symmetric with n by 1 column vectors, x and I. Then if we were to take x and transpose it, right, make it a row, as if it's a column vector, and transposing would make it a row vector, times A times y, it would be equivalent to taking y transposed times A times x. All right, so, and then we have a theorem that says let A be a real symmetric matrix. So it's symmetric with all real numbers in there. Then all of the eigenvalues of A are real with real eigenvectors. Eigenvalues are real with real eigenvectors. And the eigenvectors that correspond to distinct eigenvalues are orthogonal. They are perpendicular. We also have another theorem that says a real symmetric matrix possesses a complete set of eigenvectors. A real symmetric matrix possesses a complete set. And in fact, it possesses a complete orthonormal set. So orthonormal says that they are orthogonal to each other and unit 1. They have length 1. So it possesses a complete orthonormal set of eigenvectors. Give you a definition real quick. We say an n by n square matrix K is called an orthogonal matrix if and only if its inverse is equal to K transposed. So if you find the inverse and it's equivalent to transposing K, then we call it an orthogonal matrix. So the result of this is that every n by n real symmetric matrix A possesses orthonormal eigenvectors with corresponding eigenvalues and an orthogonal matrix K such that K inverse is equal to K transposed, which then means that if you switch out that, remember from yesterday, we had K inverse times A times K was equal to the diagonal of all the eigenvalues. So now we can actually replace K transposed. This is only for when it's symmetric. Right? Don't do it if it's not a symmetric matrix. It's not true, right? But if your matrix is symmetric, which means if you switch rows and columns, they're equivalent, then we've got this. So that helps us out. We end up not having to find the inverse of K. We can just use K transpose, which is so much easier, right? Okay, so let's do some examples. We've got, for each matrix A, we're going to verify that A is symmetric. We're going to find the eigenvalues and eigenvectors of A. And we're going to find the orthogonal matrix K and diagonal matrix D such that that's true. And we also are going to show that K inverse is equal to K transpose. Okay, so let's do an example. Do example one first. All right, example one is A is 2, 2, 2, negative 1. Now, so the first thing they want us to show is show that it's symmetric. Well, to show it's symmetric, then that means we need to show that A is equal to A transposed. So let's start with what would A transposed be, right? So A transpose means I'm going to take row 1 and it'll become column 1. And I'll take row 2 and it will become column 2. And that's what A transpose will be. All right, so row 1 is 2, 2. That's going to become my first column. And row 2 is 2, negative 1. That'll be column 2. Yeah? And then we compare and we're like, ooh, look at that. They're equal. Yeah? It's equal to A, check. That's all you're going to do to show it's symmetric. Do the transpose, show that it's equivalent to A, and you've shown that it's symmetric. All right, then when we go to find, the next thing they want us to find are the eigenvalues and eigenvectors. So to find the eigenvalues, remember you need to do lambda times the identity matrix minus A, which will give you lambda minus 2, 0 minus 2, 0 minus 2, and then lambda minus negative 1. And then your characteristic polynomial will be the determinant of this guy, which will be lambda minus 2 times lambda plus 1 minus negative 2 times negative 2, so that's a positive 4. When you multiply those out, you'll get a lambda squared plus 1 minus 2, so a minus lambda minus 2 minus 4, so minus 6. Well, that factors as lambda minus 3 times lambda plus 2. And to get our eigenvalues, you set this equal to 0. And so you've got one eigenvalue of 3 and your other one is negative 2. Both of these have a multiplicity of 1. I'm not even going to bother writing it because it didn't ask me to say the multiplicity. So there you go. So those are your two eigenvalues. To find the eigenvectors, we just plug these values into this matrix here and solve. So for when your eigenvalue is 3, your matrix would be 3 minus 2, which will give you 1, and then a negative 2, a negative 2, and then 3 plus 1 will give you 4. We're solving for when those guys are 0. I want to zero this guy out, so I would do a 2 times row 1 plus row 2. Give you a 2 plus negative 2, negative 4 plus 4, and then a 0 plus 0. So that first row tells me x1 minus 2x2 is equal to 0, which means x1 is equal to 2x2. And so I'll let x2 equal a, then x1 will equal 2a, which means my eigenvector would be 2a comma a, factoring out that a, we get 2 comma 1. Now, they're going to want us to have not only the orthogonal, but orthonormal. So let's find that, the unit eigenvector. And remember, you find it by dividing by its magnitude. So I'm going to call it K1. it's equal to 2 comma 1 divided by the magnitude of 2 squared plus 1 squared would give you 5. All right, we're going to do the same thing, find the eigenvector for when your eigenvalue is -2. When lambda is -2, I'll have a -2 minus 2 is -4, and then a -2, and a -2, and then a -1. All right, and then I don't know when these are 0, so I would do row 1 plus a -2 times row 2 to give me -4 plus +4, -2 plus +2, and a 0. You could go and divide by 4. I'm just going to leave it like that and go, okay, this first line tells me -4x1 minus 2x2 is equal to 0, which then means that x2 has a smaller one. So I would add that 4x1 over there so that x2 would equal -2x1. So by letting x1 equal a, then x2 will equal -2a. So that my eigenvector will be a comma -2a, which means it's a times 1 comma -2. And then the unit eigenvector, call it K2, would be just 1 -2 over its magnitude, which would be the square root of 1 squared plus -2 squared. So you get 5. All right, so those are your eigenvalues and eigenvectors. The next thing they wanted us to find was find orthogonal matrix K and diagonal matrix D. So K, remember, is just, you take your eigenvectors and put them in columns, and that'll be your vector or your matrix K. So 2 over rad 5, and then a 1 over rad 5. And then your second column will be this guy. So 1 over rad 5 and a -2 over rad 5. Yeah. And what this theorem that we have now says is that because this matrix was symmetric, that it'll turn out that you could go and find the inverse of this guy, but this new theorem says, hey, K inverse is K transposed, right? And so if I transpose this matrix and make row 1, column 1, it would be 2 rad 5, 1 over rad 5, and then make row 2, column 2, 1 over rad 5, and a -2 over rad 5. So this theorem says these two should be equivalent. So they want us to verify. Let's verify that K transpose truly is the inverse. And you do that by taking this K transpose, multiplying it times K, and you should get the identity matrix. And so that's what we'll do to verify. So they asked us to verify that KT is equal to K inverse, right? So you do it by multiplying transpose times K, which is 2 rad 5, 1 over rad 5, over rad 5, -2 over rad 5, and then times K. All right, so we'll multiply these two by doing, you'll go row 1 times column 1. So you'll have a 2 rad 5 times 2 rad 5, 2, or not 2 rad 5, but 2 over rad 5 times 2 over rad 5, plus 1 over rad 5 times 1 over rad 5. That'll be your first row, first column. To get row 1, column 2, you'll multiply row 1 times column 2. So 2 times rad 5 times 1 over rad 5, 2 over. Yeah, here, I'll make you feel like we're normal in class. Cheers. Coffee. Yay. Okay. Times 1 over rad 5, and then plus 1 over rad 5. I saw on the screen, yes. Times a negative 2 over rad 5. All right, and then we do the same thing with row 2 and column 1. That'll be a 1 over rad 5 times a 2 over rad 5 plus negative 2 over rad 5 times 1 over rad 5. And then bottom corner here, row 2, column 2. So a 1 over rad 5 times a 1 over rad 5 plus negative 2 over rad 5 times a negative 2 over rad 5. All right, let's simplify it. That's a 4 over 5 plus a 1 over 5. 4 over 5 plus 1 over 5 is 5 over 5. So that's going to give you a 1. Yay! This guy, 2 over 5 plus a negative 2 over 5. That's a 0. 2 over 5 minus, sorry, that was messy, minus a 2 over 5, 0. And then a 1 over 5 plus a 4 over 5. 5 over 5 is 1. That is the identity matrix. And so you have just verified, yep, for sure. K transposed is K inverse because K inverse times K, when you get the identity matrix, it says those are the identities. Or that's when you multiply and you get the identity matrix, then they're inverses, yes? All right, so then they also wanted us to find D. This was still part C, I think. Yeah. Okay, so they wanted us to find K. They wanted us to show that K inverse was equal to KT. I just did it. That was that part. They also want the diagonal matrix. So the diagonal matrix, remember, is the diagonal matrix where down the diagonal are your eigenvalues. And our eigenvalues were 3 and negative 2. So there it is. And remember, D is equal to, and I'll show it in case, I think we do have you verify that D is actually what it's supposed to be for a 2 by 2. So let's do it. Remember that D is supposed to be the matrix that you would get if you did K inverse times A times K. So I'll verify it. Since it's a 2 by 2, it's not too bad, right? So this would be K inverse was 2 over rad 5, 1 over rad 5, 1 over rad 5, negative 2 over rad 5. A was a 2, 2, and a 2, negative 1. And then K was a 2 over rad 5, a 1 over rad 5, 1 over rad 5, and a negative 2 over rad 5. Okay, so let's multiply these. Here's what I'm going to do to make my life easier. I can factor out that 1 over rad 5 from this entire matrix. I can also do it from this entire matrix. Yeah? So that's what I'm going to do just to make my computations easier. I'm going to factor out 1 over rad 5 from this guy so that now it'll be a 2, 1, 1, negative 2. Just factoring it out. I'm going to leave, that one's nice, I'll leave that one. I'm also going to factor out the 1 over rad 5 from this matrix also. And then I've got a 2, 1, 1, negative 2. Okay, and then that way it'll just make my computations easier. Plus now this is just a 1 over 5. Nice. Yeah. If we multiply these two together, you'd have a 4 plus 2, so a 6. 4 plus -1 would be a 3. 2 plus -4 would give me -2, and then a 2 plus 2 will give me 4. And then times the 2, 1, 1, -2. And then multiply those two together. So we're going to leave this 1 over 5 out front. We got 12 plus 3 would give me 15. 6 plus a -6 is a 0. -4 plus 4 gives me 0. -2 plus -8 would give me a -10. And when you distribute that 1/5 in there, you'd have a 3, 0, 0, -2. Ta-da! That is what we said our D was. So, there you go. Remember that D is going to be the diagonal matrix. So everywhere is 0 except that main diagonal, where that diagonal will be your eigenvalues. Might have you verify it, but that's just a matter of multiplication. I don't think we have you verify a 3 by 3 because it's a lot more work. It still can be done, but it's kind of time consuming. So, okay, there we go. That was example 1. Let's do the next example. And that is where A is 0, 0, 3, 0, -2, 0, 3, 0, 0. Obviously, when on this, you can do it by inspection also, right? 0, 0, 3, yep, 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 right? You can kind of look at it too. But we do have you verify as part of A. So verify that it's symmetric. And it is symmetric if A transposed is equal to A. Now, so let's do A transposed. I'm going to take row 1, make it column 1. So 0, 0, 3, 0, 0, 3. Row 2, make it column 2. So 0, -2, 0. And then row 3, make it column 3, 3, 0, 0, 3, 0, 0. Compare. Boop, boop, boop. That is equal to A. Verified. Golden. All right, now we're going to find the eigenvalues. And to do that, I need lambda times the identity matrix minus A. So it'll be lambda minus A is up here. Well, I guess it's the same. I can look at that. Okay, so lambda minus 0 is lambda. 0 minus 0, 0 minus 3. 0 minus 0, 0 minus -2. Get to this one. They're the same, so lambda plus 2. And then 0 minus 0, 0 minus 3, 0 minus 0, lambda minus 0. All right, so there's that. And then remember that your characteristic polynomial is what you need to find, and that's the determinant of this guy. We got this 0, so that's nice. So I'll take lambda times, it would be lambda plus 2 times lambda minus 0. And then technically it's a minus 0 times blah, blah, skip it. And then a plus, now that's a -3 times the determinant of these guys, which would be 0, 0 minus, and then it's a lambda plus 2 times a -3. All right, so what have I got here? First guy, that's a lambda squared times a lambda plus 2 minus 0. Okay, then I've got a, this would be what? A +3 lambda plus 6, just for this part. -3, yeah. Okay, and then I'm multiplying that times a -3. So I would have 9 lambda minus 18. I guess maybe I didn't want to do that. I got a lambda plus 2 and a lambda plus 2 there. Okay, I'm going to factor it out of here. I'm going to factor out a lambda plus 2. Now, factoring by grouping. All this algebra. All right, so if I factor out a negative 9, I would be left with a lambda plus 2 there. All right, so then now I've got a lambda plus 2 in common, factor that out. And then the other factor would be lambda squared minus 9. Will you remember factoring? And then lambda squared minus 9 is the difference of two squares. So that means I've got lambda plus 2 times lambda plus 3 and lambda minus 3. And setting each of those guys equal to 0 will give me my eigenvalues of negative 2, lambda 1. Lambda 2 would equal negative 3, and my third eigenvalue would be positive 3. There's your eigenvalues. Now we find the eigenvectors. So for when your eigenvalue is negative 2, you're going to get a negative 2, 0, negative 3, 0. Ooh, negative 2 plus 2 gives me a 0, 0, negative 3, 0, negative 2. Yeah. How about if I do, I'll get this guy to be a 0. So I need a negative 3 times row 1 plus a positive 2 times row 3. So that I'll get a positive 6 minus 6, 0 plus 0. Positive 9 minus 4 will give me a 5. And then 0, 0, 0, 0. And I'll just leave this guy. Okay, so first row gives me that negative 2x1 minus 3x3 is equal to 0. And the third row says 5x3 is equal to 0. So this one says x1 is equal to negative 3 halves times x3. And x3 is 0. But then if x3 is 0 on this one, the next one is also 0. But then it didn't give us any information about x2. There's no restrictions on x2. x2 can be anything. You can be anything. No. All right, so what does that mean? My eigenvector will be a 0, an A, and a 0. Which means when I factor out the A, I'll have a 0, 1, 0. There's your eigenvector. We want the unit eigenvector for K. And that will just be a 0, 1, 0 over its magnitude, which will just be the square root of 0 plus 1 squared plus 0. And so it's just over 1. Doing when your eigenvalue is negative 3, I'm going to let you work it out. Okay, you'll have a whole bunch of math magic that happens in there, right? You'll end up getting that x1 is equal to negative x3 and x2 is equal to 0. Math magic. You'd always pause it, do it on your own, come back and check. Your negatives might be different, but you should definitely get this relationship now. And so that you've got a, if I let x3 be a, then x1 will be negative a, 0, a. So that when you factor out the a, you got that. And so K2, the orthonormal one, right? We need to have a unit vector there. Would be negative 1, 0, 1 over the magnitude of negative 1 squared plus 0 squared plus 1 squared. We give you 2. And I'll do the same thing or eigenvalue positive 3. Pause the video right now, work it out on your own. Yeah, and then you should get, did you pause it? Did you do it? Practice it. You should have gotten a relationship of x1 is equal to x3 and x2 is equal to 0. So an A0A, factoring the A out, 1, 0, 1. And so K3, the unit eigenvector, would be that guy. All right. Okay, so those are your eigenvalues and eigenvectors. The next thing they want us to find is the orthogonal matrix K. So for part C, K is just these orthonormal vectors. Yeah. So the first one was a 0, 1, 0. Remember, you're making them your columns. The eigenvectors are becoming your columns now for this matrix K. Negative 1 over rad 2, a 0, and then a positive 1 over rad 2. And then the third one is this guy. So a 1 over rad 2, a 0, and a 1 over rad 2. And then your inverse, remember, is equal to transpose matrix. So I'm going to make row 1, column 1. So it'll be a 0, a negative 1 over rad 2, and a positive 1 over rad 2. Row 2 becomes column 2, 1, 0, 0. And row 3 becomes column 3, 0, 1 over rad 2, 1 over rad 2. And let's verify that K transpose truly is, right? We want to make sure that we didn't make some type of typo, right? Because if you make a typo and make a mistake somewhere and you claim this, then it's not true, right? But we just do it by multiplying K transpose times K, and it should equal the identity matrix. So I'm going to be multiplying K transposed, 0, 0, and a 0, 1 over rad 2, and a 1 over rad 2 times K. All right, and then we multiply row 1 times column 1. So a 0 plus 1 plus 0, 1. Row 1 times column 2 would be a 0 plus 0 plus 0. Row 1, column 3, 0 plus 0 plus 0. All right. Row 2, column 1, 0 plus 0 plus 0. Row 2 times column 2 would be a positive 1/2 plus 0 plus a positive 1/2. 1/2 plus 1/2 is 1. Row 2 times column 3, negative 1/2 plus 0 plus a positive 1/2. That's 0. Row 3 times column 1, 0 plus 0 plus 0. Row 3 times column 2, negative 1/2 plus 0 plus a positive 1/2. Negative 1/2 plus positive 1/2 will give you 0. And then this one will be a 1/2 plus 0 plus 1/2. 1/2 plus 1/2 is 1. And that is the identity matrix. Check, you have verified it. And then your diagonal D is the diagonal matrix made up of the eigenvectors down the diagonal, and our not eigenvectors, eigenvalues. Eigenvalues go down the diagonal. So -2, a -3, and a 3, and a womp womp, and a womp womp, and a womp. There you go. And of course, you could verify it by taking K inverse times A times K, and it'll give you this guy. Right? Okay, one more example. And yeah. So example 3 has that matrix A is 4, -2, -2, -2, 4, -2, and then -2, -2, +4. So the first thing is, let's show that it's symmetric. And you're going to show symmetric by showing that A transposed is equal to A. So what would A transposed be? We're going to take row 1 and make it column 1. 4, -2, -2. Take row 2 and make it column 2. -2, +4, -2. Take row 3 and make it column 3. And then verify. Womp, 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 womp. Check. We have confirmed that it is. No? All right, then part B wants you to find the eigenvalues. So let's start with lambda times the identity matrix minus A, which would be a lambda minus 4, 0 minus -2, 0 minus -2, 0 minus -2, lambda minus 4, 0 minus -2, 0 minus -2, 0 minus -2, and lambda minus 4. All right. Let's, so that you don't end up having to have 3 terms, let's zero something out. I'm going to zero out this guy right here, just to make your computations easier when you go and have to find the determinant and stuff. So I would do negative row 2 plus row 1. You get just one of them 0. And so it's a -2 plus lambda minus 4, which will give me now a lambda minus 6. Negative lambda plus 4 plus 2, so it's a negative lambda plus 6, and then a -2 plus 2 gives you 0. The rest of the rows will stay the same because that's the only one I'm going to change. There we go. All right, so that your characteristic polynomial is the determinant of this matrix. So I'm going to take this lambda minus 6 times the determinant of this minor here. So it'll be a lambda minus 4 times another lambda minus 4 minus 2 times 2, +4 there. You're subtracting 4. And then it's a minus the negative lambda plus 6 times, what would that be? 2 times lambda minus 4 minus, minus a 4. Okay, so then let's clean this up. I've got a lambda minus 6 here. This guy would be lambda squared minus 8 lambda plus 16 and then a minus 4, so a plus 12. When you distribute this negative, it becomes a positive lambda minus 6, distributing the negative inside there, and then times 2 lambda minus 8 minus 4, so a minus 12. Okay. Factoring by grouping, I have a lambda minus 6 in both of these terms, so let's factor that out. I would be left with a lambda squared minus 8 lambda plus 12 plus 2 lambda minus 12. Combine like terms here and get a lambda minus 6 here. Here I'll have a lambda squared minus 8 lambda plus 2 lambda will give me a minus 6 lambda plus 12 minus 12. Nice. Yeah. I can factor out the lambda in common here, which will leave me with a lambda minus 6. So I end up with a lambda times lambda minus 6 quantity squared. There you go. There it is factored. For those eigenvalues, you're going to set this equal to 0 so that you've got lambda equals 0 or lambda equals 6 with a multiplicity of 2. This guy's just a multiplicity of 1. Lambda equals 0. All right. So I'm going to do some more math magic now, because I feel like I need to look at the time of what time I start recording, because I feel like this recording is going too long. All right, here we go. When lambda equals 0, you're going to get a bunch of math magic. Math magic. Pause the video now, work it out. You should get the relationship of, hopefully you paused, hopefully you worked it out. Welcome back. x1 is equal to x2, and you should also get that x2 is equal to x3. So that means you'll have an eigenvector of 1, 1, 1, and so the orthogonal one, right? Orthonormal, right? We want the unit 1. So 1, 1, 1 divided by its magnitude, which would be about 3. Okay, when lambda equals 6, you will end up with, you should end up with top row being like a 1, 1, 1, and everything else is zeros. And so, again, math magic happens, and you get x, the top row should be the relationship of x1 plus x2 plus x3 is equal to 0. Yeah, which means x1 is equal to a negative x2 minus x3. No relationship between those. So you got to let them equal different values. Yeah, so I'm going to let x2 equal a. I'm going to let x3 equal a different letter because there was no relationship between them, right? And then that means x1 will be negative a minus b, so that your eigenvector will be negative a minus b, a, and b. We should make the statement that a and b not both 0. One of them can be 0, but if they're both 0 at the same time, you're just getting the 0 vector. So, okay. So, a and b can be anything, right? A is any real number, b is any real number, as long as they're both not 0 at the same time. So, here's where you get to get creative, yeah? Choose a number. Pick a number, any number. I'm going to go with easy ones, yeah? I'm going to let a equal 1, and I'm going to let b equal 0, because why not, right? A can be anything. This is just the relationship, right? It can be anything. So, what would that give me? That would give me a negative a minus b would give me a negative 1 minus 0. A is 0, or I'm sorry, a is 1, I said, and b is 0. So there is a relationship between them, not the only one, right? Obviously, since a can be anything and b can be anything. Okay, as long as they're both not 0 at the same time. And so K2 is negative 1, 1, 0 over its magnitude, which would be rad 2. Okay. So what we need is for we're saying that these guys are orthonormal, right? And we need K, we need K1, K2, and K3. We need 3 since we had it's a 3 by 3. Also, our multiplicities add to 3. And so we need K3 to be orthonormal to both K2 and to K1. And so what I need is, I activated Siri. I don't know how, but I need the dot product of K2 and K3 to be 0 so that they're orthonormal, right? So what I'm going to do is take K2, which is, and I can leave out the override 2 for right now, and just do -1, 1, 0, do the dot product of that with -a minus b, comma a, comma b. And I want, when is this equal to 0? To get another orthonormal. All right, so dot product is multiply -1 times the first guy, and then plus a 1 times a, and plus a 0 times b. And that'll give me a positive a plus b plus a plus 0 equals 0, which means b is equal to -2a. And so if I plug that in to my relationship here, I would have a -a minus -2a, plugging in a -2a into b. And then it was an a, and then b we said was -2a. And then simplifying that would give me an a, -2a, which gives me 1, 1, -2. So that K3 would be 1, 1, -2 divided by 1 squared plus 1 squared plus 2 squared, which will be what? 6. Yeah, that's how you'd find the third one. And big K will be, you take your eigenvectors, these orthonormal eigenvectors, right? And you make them your columns. So K1 was, must have been 1 over rad 3, 1 over rad 3, 1 over rad 3. K2 was a -1 over rad 2, a positive 1 over rad 2, and then a 0. And then K3, 1 over rad 6, 1 over rad 6, and -2 over rad 6. And then you'll just continue like the others, right? Your D is your eigenvalues. So, okay, all right. That was section, what was it, 4.4. And there, go back to, come here. Stop presenting. All right, hope y'all have a good day. Yes, stay up on it, because who knows what is happening. I don't know what's going to happen. But let me know if you guys need to chat. I'll come and meet with you over here in Google Meet or something, okay? All right, have a good day. Bye.